Hello, and welcome to this video on Liberty ship failures during the Second World War. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business on the web at welding-consultant.com, and you're going to find this video on my YouTube channel at Weld Nugget. So Liberty ships were used for cargo transport during the Second World War, and they were also used for troop transport. 18 shipyards built a total of 2,700 ships from 1941 to 1945, which is an astounding rate of 10 ships a week. In the photograph above, you can see the SS Jeremiah O'Brien, which is as a museum right now at Pier 35 in San Francisco. I believe there are 3 other similar ships at different locations that you can visit. During Second World War, President Roosevelt said these ships would bring liberty to Europe, and hence the name Liberty ships. There's another variant of Liberty ships, which was the T2 tanker, which was an equivalent, and that was designed to carry fuel. The unique aspect of Liberty ships was these ships were welded instead of riveting. So prior to Second World War, the ships were always riveted, but in the process of trying to make ships faster and cheaper, riveting was taking too much time, so they converted to welding instead. Unfortunately, quite a few ships had issues. This one shows over here a photo of SS Schenectady, which just split open in 1943 while sitting in the harbor. Cracks in hulls and decks were a common issue, with 1,500 significant issues reported. And in some cases, up 12 ships actually broke in half without any warning and sank, leading to a lot of loss of life. Because one of the major differences in production of these ships was the fact that they were being welded instead of riveted, the initial suspicion fell on welding as the root cause of failure. As usual, experts got involved, and the main person in charge of this investigation was Constance Tipper, and she investigated the failure of Liberty ships. She was the first female full-time faculty member at Cambridge University Department of Engineering. She was a metallurgist studying metal strength and effect on engineering structures. She was also the first person to use scanning electron microscopy to study fracture surfaces. In honor of her contributions to this effort, the Constance Tipper Silver Medal is awarded every year to scientists and engineers making significant contribution in the field of fracture of materials. So what was her conclusion from this investigation? She concluded that welding was not the root cause of failures. While welding processes and controls needed to be improved, the welds themselves were not causing the failures. This was the first time that mass-produced and prefabricated plates were being welded, and it was likely that poor fit-up and heat-related distortion were contributing to stress due to welding. However, the cracks did not appear to initiate at welds nor travel along the weld seam. So where did the cracks initiate? The crack initiation was found to happen at sharp corners, at square hatches and portholes. So back in the day, these square hatches or door frames and portholes had sharp corners, and these sharp corners it resulted in being stress risers, and under the right circumstances, a crack would initiate from these locations. Since the Liberty ship disasters, all the ships now you will find have rounded hatches and ports as shown in this picture above. I could not find a picture of the square hatches and round ports from the Liberty ship era itself. However, the cracks themselves did not cause such a massive disaster. The root cause was the brittle steel at low temperatures. So what her investigation revealed that most of these ships failed in the cold winter months. So some were actually failing right in the harbor itself. Since the ships were welded construction, cracks could grow all the way to complete failure. So one of the benefits of riveted construction is that if there is a crack in one of the plates, and let's say two plates are joined by riveting, if the crack is on one of the plates, the crack gets arrested when the crack reaches the end of that plate. However, when you weld a structure together, the entire structure becomes a single piece in some sense, and the crack can actually travel from one part through the weld into the other side and continue to grow. So the main issue was, why are these cracks growing so quickly? And she found out that the steels were becoming too brittle close to freezing temperature. So these steels were ductile when measured in the lab at room temperature, but close to freezing point, these steels were behaving in a very brittle manner. To measure the temperature transition, Constance Tipper introduced the Tipper test, which is now used in the form of a Charpy impact test to measure now what we call ductile to brittle transition temperature. So how do we do that testing? To take a piece of steel for testing, it is machined into small pieces, which are 10 by 10 by 55 millimeter rectangular sections, and one of the faces is machined with a V notch. That sample is now placed in the machine with the V notch facing in the opposite direction as from when the pendulum is coming down. And there's a heavy pendulum with a bar, and that pendulum is launched or started from a certain height, and that height is proportional to its energy. Once the pendulum is released, it goes through the sample, breaking the sample and reaching the other side. So the difference in height between the initial height of the pendulum on one side, the starting point, and the final height on the other side at the end of the test, that difference is a measure of loss of energy which was required to break that sample. And that energy is calculated as the impact energy in foot-pounds, which is same as joules. So what you can do is take a type of steel, if you want to do the DBTT testing, make multiple coupons, hold them at different temperature, and test them. And then you can plot this curve over here, which looks like an S shape in case of carbon steels. So again, different materials and metallurgies will have different shapes. But for carbon steel, that is a typical shape. As the temperature goes down, the energy required to break that sample goes down, and you can plot a chart like that. Usually, the energy of 20 foot-pounds corresponds to a certain temperature on that curve, and that temperature is listed as the ductile to brittle transition temperature. This is just a way of comparing multiple steels, and so that has been used as a number. And in this case, if you look at this chart, the 20 foot-pound energy loss during testing occurs at 0 degrees centigrade. So this would be similar to a steel from, say, Liberty ship, where it undergoes that ductile to brittle transition temperature. If you're able to improve the metallurgy of that particular steel, then that curve will shift to the left, and the ductile to brittle transition temperature will reduce, go down, -10. We actually have gone down much lower than that. And here I'm going to show you on the next slide a comparison of different ship steels. No discussion of ship failures is complete without the mention of the Titanic, which sank in 1912. The difference between Titanic and the Liberty ships was the Titanic was of a riveted structure, but still, it was still affected by the ductile to brittle transition temperature, as it split open much easier than was anticipated. They have done some chemical analysis on the steels from Titanic and the Liberty, and they have actually done ductile to brittle transition temperature testing on the Titanic as well. It was found to be about 50 degrees centigrade positive. And give you the chemical analysis: carbon, manganese, and sulfur and phosphorus. The main numbers, two elements to keep track of, is manganese and sulfur. So back in the day, manganese was only 0.5% and sulfur was 0.065. As the time of Liberty ships came into play, The manganese had already been increased to 0.75. I could not find data for the sulfur, but the ductile to brittle transition temperature has been reported to close to 0 degrees centigrade, as close to freezing. Modern ships have different grades of steel now available for different applications. So if a ship or a marine structure has to be used in the tropical environment, they will use a typical A36 steel, which is essentially a carbon steel. Carbon is used for strength, and then you have higher levels of manganese than before and lower levels of sulfur. If the ship has to be used for colder climates, a modified version is available at AH36 and with a ductile to brittle transition temperature of -40. So A36 at -13, AH36 now at -40. And you can see that the manganese levels have increased and the sulfur levels are lower. And finally, there is another grade called FH36, which is used for polar applications. And the transition temperature is down to -60. Here again, we see the manganese has gone up and the sulfur level as requirements has gone down. In reality, these numbers are now much lower, sometimes much lower than 0.025, down to like 0.01, 0.008. And that really helps in reducing the transition temperature. So the two main elements which affect that transition temperature is increase in manganese and reduction in sulfur. So sulfur reduction is the most important. The manganese is actually added because manganese can bond with the sulfur and keep it out of trouble. So manganese is essentially added to reduce the detrimental effects of whatever little sulfur is there. In modern steels, you will find that if you go from this tropical to cold to polar applications, we find that there is a reduction in carbon as well, which also makes the steel more ductile. But at the same time, you want the strength in the steel, and that's why scientists have added a whole bunch of other elements, micro-alloying elements. So all these elements combined are less than 2% in the steel, and hence these steels are called high-strength, low-alloy steels. Now, these three modern steels which I have listed are just an example. There are many other similar grades and varieties of these steels, but essentially the job is the same, that depending on the certain application, depending on the location where these steels will be used, you have to choose the right steel with the right ductile to brittle transition temperature. So what was the sequence of events in Liberty ship failures? So the first and foremost, we have to have a crack which can grow, and the cracks would initiate at sharp corners, and these typically ended up initiating around these square hatches and ports. The second thing is cracks had to grow rapidly, and for that we needed a brittle steel. And at low enough temperature and cold weather, the steel would become brittle. And once the crack initiates, the crack would grow very rapidly. Because it was a welded structure, the cracks also jumped across welded plates. So that is one of the downsides of welding, is if the crack starts growing and you cannot stop it, it will jump across plates and go all the way to the end. And this would not have happened on a riveted structure. Depending on location and direction of the crack, there were situations where it was a catastrophic failure and the ships would literally break into half and sink within minutes. So what were the remedial measures taken on the Liberty ships? First was to lower the ductile to brittle transition temperature by improving the quality of the steel. The second was to round off the hatch corners. So of all the ships, some of the ships were already made. So what they did is they actually put patches on these corners, welded patches on all these corners to prevent the stress from opening up a crack at that location. Later generation designs already had round corners. So further after Second World War or halfway through Second World War, all the ships from there on always had rounded hatches and corners. Again, with many of these ships already being made, they actually had to install crack arresting devices, which were essentially riveted straps. So especially at critical locations, they actually put riveted straps to arrest these cracks from growing. So almost like a Band-Aid type solution, but it worked. And of course, they also improved the welding practices and established welding codes. Due to the importance of the contribution of Liberty ships to the Second World War effort, a stamp was issued on February 26, 1946 to honor the merchant marines' achievements in this war. And the stamp actually shows a Liberty ship unloading its cargo uh, back in the day. For references, I've used Wikipedia and search on the internet. There's a good article on metallurgy of RMS Titanic. And for commercial steels, information is available on the web. One of the, I wouldn't say benefits, or one of the outcomes of these Liberty ship disasters was this led to significant improvements in the field of welding, fracture mechanics, material testing, and manufacturing. So a lot of the things which we see today have their foundation back in the day during this experience with the Liberty ship failures. Well, I want to thank you for your time. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking on the subscribe button. You might find that on the bottom of your left hand of your screen or the right corner, depending on which device you're using. There are multiple videos in different playlists on my YouTube channel, including those for laser welding, arc welding, resistance welding, other welding processes, metallurgy, and design. I hope you find them to be useful, and I want to wish you the very best in your efforts to learn about welding and joining. Take care, and thank you.